Good morning, students. So last class we have discussed regarding different types of radius ratios and relation of radius ratio between the structure of the compounds, coordination numbers. Now we have to discuss regarding some crystalline solids and their arrangements. Okay. So let us look here, sir. Whenever we have to arrange the solids, the arrangement may be different types. Just we have to see it is in the close packing time. I say this may be 1 dimension, 2 dimension, 3 dimension, but actually the structure of a solid is found to be formed in 3 dimensional manner. Previously that we know, because in 1 dimension it will become a line, just a line-like structure, where the solid structure is not possible. In 2 dimension it will seed-like structure, where is the solid also not formed. Only in 3 dimensional structure you will see that there is a length, breadth and height. That's why a complete solid structure we can obtain. And this 3 dimensional structure also, I told you, it is 2 types. One involving square close packing, another involving hexagonal close packing. And once again, in hexagonal close packing we have to see also CCP type as well as BCC types. Okay, CCP and HCP type. Now you see in these ionic solids, let us the structure may be chemical formula may be AB or it may be AB2. So what happens? AB means 1 cation and 1 anion is there, and if it is AB2, then 1 cation and 2 anions is there. Okay, so in this context we can see the structures, coordination number, radius ratios, all these things are found to be different whenever we will go a crystalline solid belonging a particular type of the structure to other different structures. Okay, so in this instance, all solids that we have to found, ionic solids are to be generated, is to be classified into 5 categories. That is, one involving sodium chloride structure, another involving cesium chloride structure, and next involving your zinc sulfide structure, and next involving calcium chloride structure. And at lastly we will get the azurite type structure. And this azurite type of structures, this is simply, we can say, this is alternative of zinc sulfide structures. So let us look here, sir. First of all, you see, whenever a ionic compound is formed, there is a cations and anions. And whenever there is a cations and anions, what happens? In these cations and anions, you can see the cations will smaller size and anions will the larger size. Okay. So while occupying these cations and anions in different position in a crystal lattice, because of the size of the cation is smaller, so it has to occupy any interstitial sites or spaces, whereas the anion occupies the main sites, face centers or elsewhere. Okay, so in these connections we have to total get 5 different type of the structures in these crystalline solids. Okay, whenever we get the 5 different structures, we see how they are arranged in which positions and what is their ratios and what is their structure compositions. We have to detail these 5 type of the structures. So let us you have to come first of all sodium chloride type of structures. So it is the most common type of the structures where the ionic solids have the structure belonging AB type. In this AB type structure, you can follow there is a 1 cation and 1 anion is there, and we have to get the sodium chloride structures. And in these structures, what are the features of these structures? It has an FCC arrangement. FCC means phase closed cubic, that is phase centered cubic structures. And here what happens, the chloride ions occupy at the corners as well as the center of the cubes. Already I told you that between the cations and anions, since the size of the anions is large as compared to the size of the cations, so anions will occupy the main positions, face positions, corner positions, whereas the cations, due to its small size, they will occupy any void positions or interstitial size positions. So now you see here, it is the FCC arrangement because the chloride ions are larger size, so they will occupy the corner as well as the center of each face of the cube. That is the part of the anion mark, or it is the chlorine mark, minus. Or if in Ag structure we will say it is A plus B minus, means B minus belonging to chlorine, minus, and A plus belonging to Na plus ions. So what will happen, sir? It is a FCC arrangement whereas the chloride ions will present at the kernel as well as the center of the cube. At the same time, the cation, that is Na plus, that occupy the octahedral sites. Okay, so I told you there are two type of the sites is formed. One is a tetrahedral sites and another octahedral sites. So in this case, our octahedral sites are formed and that sites are occupied by your Na plus ions. So what will happen, sir? The Cl minus ion, chlorine minus ions, they are present at the kernel position as well as the center of the cube. Whereas the Na plus ions, they are present at the octahedral sites. Okay. So while arranging these cations and anions, so what happens, sir? Each Na plus ion is surrounded by 6 Cl minus ions. Simultaneously, each Cl minus ion is surrounded by 6 Na plus ion. So we can say the coordination number of Na plus ion as well as Cl minus ion is 6. So hence we can say here the coordination number or the ratio is 6 to 6. Each Na plus surrounded by 6 Cl minus, each Cl minus surrounded by 6 Na plus ions. Now you see in this arrangement there is a octahedral site per atom. So Na plus and Cl minus ratio we have to form 1:1. Okay. Once again, if we go regarding the radius ratio, what is radius ratio? It is the ratio of the radius of the cation to radius of the anions. As you know, the size of the anion is greater than the size of the cations. So it is always mostly remain less than 1, or it will maximum up to 0.999. So in this case, the size of the cation, look here, 95 pm, that is size of the sodium atom, and 181 pm, that is the size of the chloride minus ions. What happens? The ratio is found to be 0.524. We already categorized in earlier classes. There is a relation between radius ratio, coordination number, and structures. So just to recollect, this number will come into 0.524, come in the middle range. The first range will come from 0.999 to 0.724. Second range will come 0.724 to 0.424. Okay, just like so. Here we can say this belongs to second range. That's why the structure is found to be cubic and octahedral types. And once again, if you say all the example, if you go the sodium chloride type, then you can say all alkali metals halides except leaving the cesium metals. All alkali metals means lithium, sodium, potassium, rubidium, cesium exception. Francium is a radioactive metals. All halides are found to be exist or show this type of the pattern. What is observed in case of the NaCl structures? In all rest of the members of the same family, alkali metals of group 1A, except cesium elements, we can find this type of the structures. Besides the cesium metals, halides, alkali metals, halides of silver also, except silver iodides, leaving iodide, silver chloride, and silver bromide, all halides of the silvers. Also, we can exhibit this type of sodium chloride type of the structures. So this is the first type which is the commonly found in all ionic compounds, maximum ionic compounds. Okay, and its characteristics is like this. We have to now presently go regarding the second type that is cesium chloride type structure. Cesium chloride type structures. Let us look here, sir. In the first case, we have to make it exceptions. Cesium chlorides exception, that is the NaCl structure. So this is a particular different type of structures as compared to your NaCl AB type structures. So in cesium chlorides, you see here the Cl minus ions arranged at the cubic structure, where Cl minus ions present at the corners of the cubes. Cl minus ions are present at the kernel, whereas Cs plus ions occupy cubic sites present at the body centers. Okay, so that is the arrangement or presence of the Cl minus ion one side and Cs plus ion on the sides. And in these structures, what will happen? So you see, each Cs plus ion is surrounded by 8 Cl minus ions. Similarly, each Cl minus is surrounded by 8 Cs plus ions. So what happens when the coordination number ratio is found to be 8:8, okay, in these compounds or in this structure, so the coordination ratio is found to be 8:8, okay. And if you go, now you see, if you count the radius ratio times, cesium is 160, that is the cationic radius ratio of the cesium cations, and Cl minus is 181, that is the anion ratio. And if you go to the range, then you will get 0.884. And its structure will become cubic type, because in the radius ratio and coordination number table we found that the first one, that is I told you several times, 0.9992, 0.732, this range will belong that category. Hence we can say this is a cubic type of structures. Just like cesium chloride, we can see the same structure is found in case of the compound cesium bromides and cesium iodides. Okay, so you see these compounds along with your cesium chlorides will show this type of the patterns, that is, you can say cesium chloride structures. Now let us you to come the structure of zinc sulfides. Okay, so zinc sulfide, here something found to be different. Okay. See, in zinc sulfide, what will happen, sir? Here also we can say in zinc sulfide, the cation is zinc and the anion is sulfur. Okay, sulfide. It is also found to be formed a cubic close packed arrangement. This is also cubic close packed arrangement where H2 minus ions form the phase centered cubic structures. In this structure, H2 minus form the phase centered cubic. The main patterns, and the G2 plus, that is we can say the cations, which is a small size that has to be present in your sites, that is you can say octahedral sites. It is occupied at the octahedral sites. So in this case, the coordination number, you can say each Zn2 plus ions is surrounded by 4 H2 minus ions. Exactly on the same way, each H2 minus ion is surrounded by 4 sulfides ions. So each Zn4 plus surrounded by H2 minus ion, each H2 minus surrounded by 4 Zn2 plus ions. So you can say the coordination number is 4:4. Okay. Next you become the radius ratio. So you see the radius of, that is the zinc plus ions, is found to be 74, and chloride minus ion is found to be 181. So this is found to be belonging to the range of 0.40. Okay, and its examples, you can say the structure will come copper chlorides, copper bromides. These structures will follow like that, or zinc sulfide structures. Okay. Now let us come the fourth category, the structure of calcium chlorides. Okay. So you see calcium chloride, what you say here, CaF2. So we can assume this model just like AB2, because there is a one cations and two anions is there. Here the cation is calcium and anion is also fluorine. So there is a ratio of one cations and two anions, that is 2 fluorine atoms. So here Ca2 plus ions present at all corners and at each center of the face of the cubes. That is the presence of the cations, and F minus ions occupy at the tetrahedral sites. Okay, and each F minus surrounded by 4 Ca2 plus ions. Similarly, each Ca2 plus is surrounded by 8 F minus ions. Okay, so here we can say the ratio is found to 2:1. Okay, one cation is surrounded by 2 anions and one anion surrounded by 2 cations, just like that. So that is the structure formed in the calcium chloride patterns. Now the last one, we can say azurite structures. So actually, basically you can say there are 4 structures. So what is azurite structure? Azurite structure is nothing only, it is the alternative structure of, we can say, zinc sulfides. Okay, in zinc sulfide arrangement, what will happen, sir? You see, it is a cubic close packed arrangement where H2 minus ion present. Okay, and Zn2 minus ion occupy the octahedral sites. But in azurite structures, this sulfide ion, which is present in cubic close packing arrangement, that we can say the pattern of ABC. Just you recall, I told it at the time of arrangement of the solids. Okay. So in a three-dimensional case, we will get two type of packing. One is ABC, another is AB. Okay. So ABC type packing belongs to the cubic close packed, whereas the AB type belongs to the hexagonal close packing. Okay. So in zinc sulfide structure, so what will happen, sir? It will come to ABC type packing of sulfide atom. But whenever we go azurite structures, that ABC will become only AB types. So basically we can say the structure zinc sulfide and azurite structure are same. Only the difference is the sulfide ion which is present here ABC pattern, which is nothing only cubic close packed arrangement, that is present in AB, that is hexagonal close packing arrangement. Okay. So basically once again in brief we can say those ionic compound, simple ionic compound has been categorized into four structures, means four patterns. So what we say, four patterns are sodium chloride type, cesium chloride type, zinc sulfide type, and calcium chloride types. Okay. So all the ionic compounds that have to follow these structures, they have to see following characteristics and occupations of the cations and anion in the respective places, their radius ratios, okay, and how the structure is found to be formed. So this is all about. So actually, basically, these cases it is important for you during the examination point of view. You have to be asked only objective questions from these sections. Means he will ask you zinc sulfide belongs to how many cations or anions is there, or give some examples of zinc sulfide structures, or he will give an example just like silver chloride and told what type of ionic structure is found to be formed, or he will ask you what is the radius ratio of cesium chloride type structure. So basically you will get the objective questions from this section only, that is structure of simple ionic compounds. Okay. Okay. Next, now let us to see regarding the properties of the solids. We have to discuss two types of the properties of the solids. One is electrical properties of solids, and second is we have to see magnetic properties of the solids. Okay, magnetic properties of solids. So basically, here we have to discuss regarding two properties of the solids, electrical properties and magnetic properties. Regarding electrical properties, if you come, then the substance is classified into three types for the solids. That you can say, what we can say, that is a conductor, semiconductors and insulators. Okay. So see what is the difference between these semiconductor and insulator. Conductors means these are the substances which will carry the currents frequently or very freely, or current can pass easily, and its range is found to be 10 to the power 8 conductivity range, ohm inverse, Cm inverse. So in case of the conductors, the current is passed smoothly or easily. And semiconductors, here what will happen, sir? The current can't pass easily or fluently, but it can pass. Okay. And its range is found to be 10 to the power minus 3 to 10 to the power 6 ohm inverse, Cm inverse. And last is the insulators. What will happen? The insulators, the current carrying capacity is very less, or it is very small, and it remains in the range of 10 to the power minus 12 ohm inverse, Cm inverse. For example, plastics, woods, okay, all these things we can say they don't pass the currents, means their conductivity range is found to be very less. Okay. So now you see what is the difference, or on which basis the current is to be passed with a conductor or semiconductor, or in insulators the current is not passed. To simplify or to understand this concept, we have to know the band theory of solids. So now you have to see what is the band theory, okay, or conduction theory. Let us look here. So I have to show these three diagrams that belong to, this is the case involving your conductors, okay, and this is the case involving your insulators, okay, and this is the case involving your semiconductors. So now let us look here, sir. What is the thing is? You see there are two figures is there. Okay. This is we can say that is field band, and the first is your empty bands. Okay. Field band means in this field band there is electrons are present, and empty bands there is no electrons are present. Okay. And this field band is responsible for the conduction of the currents. In case of the conductors, if the field band has the few electrons or some electrons and some spaces is found to be remain empty, then what will happen is the current can be flow with these conductors. Okay. So you see regarding the conductivity, we can say the conductivity can be takes place in your metals, and also we can say the conductivity also takes place in the liquids also. Okay. In metal it is, we can say, metallic conductance, but whenever it is takes place in a liquid, that is, you can say, electrolytic conductance. So electrolytic conductance, what concerns the mechanism of the conducting in metallic conductance and electrolytic conductance is found to be different, because in electrolytic conductance an ionic compound has to be carry the currents, and what happens when we put the ionic compound, they will split, forms the cations and anions, and the cations loses electron, goes towards the anion. Okay, so that current will carries due to flow of the electrons. But in case of the metallic conductance, what happens? The electron has to be jumps or go from one place to another place, so that current can carries. So whatever it may be the electrolytic conductance or it may be the metallic conductance, the current flow due to the movement of the electrons. That is the one thing. Whether it may be your electrolytic conductance or it may be our metallic conductance. In case of the electrolytic conductance, it moves to the liquids. In metallic conductance, the electron can flow and jumps from one place to another place. Okay. So now you see in the metallic conductance, the metals are the solid substance, that is, you can say, present in the solid states. But electrolytic conductance is completely present in our liquid states. Okay, solution states. So since this is in a solid state, and here we have to discuss regarding the conductivity process. So we can say our conduction carrying process will take place, and three types of the conducting materials are formed, that you can say conductor, insulator and semiconductors. Okay. So in conductor what will happen, sir? There is the band, there is two bands is formed. One is a field band and there is an empty band. Okay. So this field band, the electrons are present, and this is responsible for the conduction of the currents. In case of the conductor, what happens? Whether the field band has some electrons, some spaces are found to be free. As a result, the electron can flow from field to on field space, so that the current can flow. Otherwise, if the field band overlaps with empty bands, you look here, there is a field band, some space is there, and it has to be overlapped here. Then also it is possible for the electron to jump from conduction band to your empty bands. As a result, the electron can flow. So in case of the conductors or full current carrying substances, the phenomenon happens by freely moving of the electrons from our field band to empty bands. Okay. Now you see, if you come to the insulators, where there is no current flows, or if it is flows, it is very negligible extent. Okay. Here what happens, the field band and empty band is found to a very large gap. Okay. Due to this large gap, what happens? These electrons at the field band can move to empty bands. Okay. Hence, the electron can jump and the current can flow also. Okay. Similarly, if you come semiconductor type, so what will happen? So here also those two bands is there. One is field band and the other is empty bands. What happens in this case? There is a small gap or little gap between your valency band and your empty band. So what will happen? Whatever it may be, the electron can jump from the valency band to your conduction bands. Okay, empty bands. Valency band to valency or field band to your empty band, so that the current can flow in a little extent. Okay. So now you see, we have to see on the basis of electron flowing in a solid, it can be classified into three categories, that is conductor, insulator, semiconductor. Our next question you see, Conductor will full extent it will carry the currents. There is no classification is required. But now you see this is the very important topic, see, because nowadays with the electric and magnetic properties we have to build the chips of the electronics which is in the main application in our electronic markets, mobile phones, computers, everything is. That's why this conductivity phenomenon is found to be very much important. So now you see, after the conductor there are some substances which is conducting more than its capacity. That means highest level, and those are we can say superconductors. Okay, but our main concern involves with the semiconductor, because we see there is two classes conductor carries currents, insulator don't carries the current, but semiconductor carries the partial current. That's why semiconductor is again classified into more types. First of all, this semiconductor we can divide into two types. That is, we can say one is intrinsic semiconductor and another is extrinsic semiconductor. Intrinsic semiconductor and another is extrinsic semiconductor. So what is now means by intrinsic semiconductor and extrinsic semiconductor? Intrinsic semiconductors, these are we can say the original semiconductors which are present the currents, okay, or which is the sufficient electron that can be carried itself, okay, it don't requires anybody's help, okay. The metal or the solid can itself will carry the currents by the availability of its saturated electrons or saturated valence cells. But whenever extrinsic semiconductors, it is not the pure conductors, okay. That means it is not the sufficient number of electrons that has to be moved for to flow. What happens with these substances, we have to make add some other substances that we can sometimes told it is doping. When doping of other materials is to be done with the conductors, then we can obtain the extrinsic semiconductors. So now you see, students, there is intrinsic and extrinsic semiconductors. Intrinsic semiconductor you can say pure type, but extrinsic is not pure types, okay. It is formed by doping with some other materials. And this extrinsic semiconductors we can say it is once again divided into two types. That is, we can say N-type extrinsic semiconductors and P-type extrinsic semiconductors, okay. So now let us look here. So what is mean by this term N-type semiconductors, P-types? So N-type we can say negatively charged, P-type we can say also positively charged. So let us look here. So I have to show you with a diagram. So how we get the N-type and P-type. See, so you have to see the N-type semiconductor and P-type semiconductor. What is difference? I told you already. In N-type semiconductors, you see there is a excess of the electrons. Now you see, generally the semiconductors are formed by group 4A elements. If you take the elements just like germanium or silicon, okay, they will generally form the semiconductors. So if you will take let us say germanium, okay, type of the semiconductors, it is found to be tetrahedrally arranged in all sides, as you know. So these germaniums that is tetrahedrally arranged in all sides, so that we will get this type of the semiconductors. So in this semiconductor, let us we have to see how it has to be formed N-type as well as P-type. See, if this germanium atoms has to be replaced by some other atoms. Some other atom in the sense, you see, they have the 4 electrons. This germanium belongs to 4 electrons. That's why they are covalently bonded with the 4 sides. You can clearly imagine that all are forming the 4 covalent bonds. Okay. Let us look here. So we have to make some foreign materials to these metals. Okay. So let us, if we take the group 15 elements and group 13 elements. Because you see, because since they are present in group 14, that is 4A, so whenever we have to make dopings, we have to do with group 15 elements, or we can do with group 13 elements. So let us look here. So we have to take a group 15 elements, and this group 15 element, let us take phosphorus or arsenic. Let us we have to take the arsenic. So what will happen, sir? Arsenic has the 5 electrons. Whenever it is the 5 electrons, so you see 4 electrons they usually bond with your germanium, and beside these 4 electrons, 1 electron remain excess in the arsenic. This is the excess electrons, and this excess electron is found to be moving around the metal atoms.
Because it is a excess electrons, so here we can say it is a negatively charged, okay, or n type or electronic type of our extrinsic semiconductors. Okay, so this is formed by doping group 15 elements to this group 14 elements. Now just like n type, if you come the p type semiconductors, you see instead of arsenic, let us we have to dope with group 13 elements. Group 13 means aluminum, borons, okay, just like this. Let us if you dope with group aluminum metals, then what will happen is group 13 elements, but in aluminum it has 3 valency electrons. Due to 3 valency electrons, it has to make 3 bonds in 3 sides, but 1 bond is found to be vacant because 1 electron is found to be shortage. So because the electron is found to be shortage, as a result we can obtain the p-type semiconductors. Okay, p-type extrinsic conductors. So now you see, if in brief we can say solid is classified in 3 categories on the basis of conductivity: conductor, semiconductor, insulators. And once again, insulator 2 types: extrinsic, intrinsic. And regarding last extrinsic conductor is once again 2 types, that is n-type and p-type. Okay, the electrons. Okay, you see, whenever an electron is revolving, it is present in a orbitals. Okay, so orbital motion is formed, and without the orbital motion, it spins towards on its own axis also. So there is a orbital motions, one magnetic moment created, and due to spinning of the electron around its own axis, another magnetic moment is also found to be formed. So due to these 2 things, orbital motions and spin motions, we will get the total resultant magnetic moments. Okay, so on the basis of these magnetic moments, basically we have to classify into 3 types these magnetic natures. What is it? You see, first of all, it is paramagnetic substances, diamagnetic substances, and ferromagnetic substances. Next, ferrimagnetic substances, and antiferromagnetic substances, So you see, on the basis of the magnetic nature, so we have to classify all these things. We know we need not to go detail about these magnetic nature so much. Just you have to know what is their natures. See, these paramagnetic natures of the magnetic compound solids has to be obtained due to presence of the unpaired electrons. And these paramagnetic natures, due to electrons they are formed, unpaired electrons, hence they are what we say weakly attracted to the magnetic field. So basically you can classify mainly say these 3 types: para, di and ferro. Paramagnetic substances, these are weakly attracted by the magnetic field, and this weakly attracted is due to the presence of the unpaired electrons in the atoms. And the diamagnetic substances, these are completely repelled by the magnetic fields. Okay, and the ferromagnetic substances, these are formed by strongly attracting the magnetic fields. So even if you take the magnetic field, also the ferromagnetic substances retains their magnetic natures. That's why, but the paramagnetic, they are found to be show the magnetic natures in presence of the magnetic field particularly, and this is formed by the atoms, ions and molecules. That's why they are very weakly attracted. But ferromagnetic, it is the particular magnetic substances, and they can retain their magnetic value for a long time. Okay, and it can be formed the metal just like iron, cobalt. Okay, just like this. And the ferrimagnetic and antiferrimagnetic, these are also formed by the presence of electrons in the orbitals. That means if they are the spins are found to be in opposite directions, then you can get the ferrimagnetic moments and resultant magnetic moment is 0. And antiferrimagnetism, here the spins are not regularly in the alternative manners, they are found to be different manners. Okay, so but in the solids point of view, if you want to know the magnetic nature, so it is very much important. That is the paramagnetic nature or diamagnetic nature and thermal. Okay, this is all about your properties of magnetic properties.